Okay, let's begin. We had a couple problems to do where you have to find the integrating factor for
the first one?
the exact equation.
Yeah, like you either didn't write it correctly or we just don't understand how to do this.
I don't know. Was it 2x squared plus y dx?
Yeah.
So you copied it down correctly?
Yes.
Oh, so it's you don't know how to do it. that answers the question, right? Because I'm pretty sure that's right.
Is it user error or program error?
I don't know. So I believe I gave you the hint for this one. Was that your mu is purely a function of x?
Yes.
So that means, so you can check, you know, my is 1, and next is 2xy minus 1, which is not equal, so you know that it's not exact as written, but you would also know that it's not separable, it's not homogeneous, it's not, well, you could probably even write it as a linear.
Try that.
You can try writing it as linear? Didn't work out?
Mine's not right though. Try something.
Okay, well, let's see. It turns out it has an integrating factor where mu is a function of x, which means, what is the formula that we need to apply here? So that is going to be, well, 1 minus 2xy minus 1 over n x squared y minus x. So you end up with, here you have 1 plus 1, so that's 2 minus 2xy. So in the top you can factor out like a minus 2, so this is equal to, if I factor out a minus 2 from the top, I get xy minus 1. If I factor out an x from the bottom, I would get xy minus 1. So this cancels. This is purely a function of x. So this means mu equals e to the integral of minus 2 over x dx is an integrating factor. And so that is e to the minus 2 ln x, or x to the minus 2. We assume that our x is positive.
You can also derive that by doing d mu dx, right?
Come again?
D mu dx is equal to mu times my minus nx divided by n. And then
Yes.
solving the differential equation.
Yeah. But we already know that once we do this, we just throw it into power e. Like we know that mu e to the integral of p, it's kind of like the same flavor here. So that should make the equation exact. So then when I multiply through by I would get here 2 plus x to the minus 2y, plus here I would get y minus x to the minus 1, dy 0. And now if I check my partial derivative of this with respect to y, I would get x to the minus 2. And if I check next, partial of this with respect to x, this comes down, becomes positive, and I subtract 1 from power, I get x to the minus 2. So now these guys are equal.
That's a quick output.
Yes?
Whenever you're dealing with LNs, so like if you have e to the negative 2 ln x, right?
Yeah.
Should you move the negative 2 to the x first? It doesn't
To
matter.
the power,
You
yes.
place the power first and then you cancel out the
Yes.
Okay.
I just skipped that section. So now it's exact, and now we can actually solve it using the other method. So f is going to be 2x plus this guy dx. It's going to be 2x minus x minus 1y plus some constant that we don't really care about. F is also going to be the integral of y minus x minus 1 dy. And this is going to be y squared over 2 minus x minus 1y plus some other constant we don't care about. This guy is redundant, he's already on there. So that means 2x plus y squared over 2 minus x minus 1y. Let's see is our solution. So where did the mistake happen?
I didn't do the factoring in.
Algebra.
Yeah, algebra is a bitch, right?
Okay. So that's the first one. Now the second example, the hint was the integrating factor is purely a function of y. So that means you kind of flip the top there and put it m on the bottom.
Yeah, nx minus my over n, right?
Yeah.
Over m. Sorry.
Over m. Yeah.
Do you have an inclination to let us know whether or not it's a function of x or y on the exam? As you did in the last quiz, I'm just wondering if that's something we should anticipate, or we could do both of them to discover which one we need to use.
I'll tell you.
Okay.
If I put a problem like this, I'll tell you, okay, there's hint, this has an integrated factor that's a function of x. I'll say something like that.
Save time.
And this one was 1 plus x minus y, x over y minus sine of y equals 0. And of course, this is just, you can make this 1 dx plus x minus y minus sine of y equals 0. If you check y, you get 0. If you check next, you get 1 over y. These aren't the same, but let's find mu. So this one isn't homogeneous, it's not linear, and it's not separable. So we'd kind of be in trouble otherwise.
If we see in that situation, if we see that nx is 1 over y, can we then think that it's more likely to be a function of y than x, or is it?
I wouldn't, no. So we are going to look at x minus my over m. This is going to look like 1 over y minus 0 over our m, which is just 1, so that's 1 over y. So this means that our mu is equal to e to the integral of 1 over y. Which is just basically y. And then multiply by y. You would end up with y dx plus x minus y sine y dy equals 0. You check mine, you get 1. Check next. You also get 1, which is equal to mine, so it's exact. And so our f is going to be equal to the integral of y dx. So I have a constant. And also, f is going to be equal to the integral of x minus y sine y dy. That's going to be xy minus, how do we do this guy?
Tabular usually.
Yeah, tabular integration by parts, either way. Just do a little tabular right here. Differentiate that, you get 1. Differentiate that, you get 0. Integrate this, you get minus cosine. Integrate that, you get minus sine. So it's, I'm ignoring this negative sign for now. This times that, so minus y cosine y. This times that is minus sine y, but I changed the sign, so plus sine y. And that's it. Plus a constant. So this means that xy plus y cosine y minus sine y. C is our solution.
Question?
Yes.
You're doing the integrated factor. How do you decide which one goes first versus n, partial of n to x and partial of m to y? How do you decide which one goes first?
Oh, well, it depends on the formula you're using. So if you know it's a function of y, or you're expecting it to be a function of y, it's nx minus my over n. You can think of it as the partial of y going last versus the partial of x going last. And of course, the guy that's last, the my, you put the original function in the denominator. When it's the nx, that's at the last part. You put the n under the denominator.
So you say whichever one you think is going to be the.
Yeah.
Okay.
But usually, in like a test, I'll tell you.
Okay.
Like if I give you a problem, I'll say, hint, this could be exact with an integrated factor if that's a function of x.
Okay, got it.
And then you'll know which one of those to actually.
Yeah, so x will go last.
Yeah. So that wraps up the exact equations with integrated factor. Now, I want to talk about some more first order situations that we can find ourselves in, just a more, another sampler here of some possibilities that are out there. Then we'll start to introduce second order equations. Today's the day. So,
Can we solve some second order by using substitution?
yeah, substitution is a general principle that might work. We're going to start out really simple, though. We're not going to need anything that elaborate for the ones that we'll be talking about today. But I want to look at some selected situations from 2.9. Solving certain miscellaneous first orders, or things that can be made first order. The first one I want to talk about is actually a situation that we will revisit later on. That's called reduction of order.
That's what I was talking about.
Right. So in 2.9, it's a very special case of that. They describe it as the, you have something like y. We're going to have a more general method called reduction of order later on. But for now, we're going to look at reduction of order in the case where where is it? Reduction of order. So we're looking at something that looks like a second order. It comes to you as a second order, but it's a function of t and y prime only. So you have no y's in the formula. And there's a very nice way to deal with that situation. Solve. We're going to do a change of variable. We're going to set b equals to the derivative. And so b prime is going to be equal to the second derivative. So I can replace y prime with v, y double prime with v prime. and I actually knock this second order down to a first order. So example. I'll only do one because, like I said, we'll revisit this. And I believe this one I put as a bonus problem on the last quiz. Something like that. So that's a second order equation because we have a second derivative there. In fact, it's a second order linear equation. But one thing you'll know is that there's no y present anywhere. You only have a y prime and a y double prime.
Yeah.
And so with that, you can just turn this guy into some other variable, and that guy's going to be the derivative of that variable. So if we set v equals y prime and v times y double prime, what ends up happening is we can rewrite this equation as v prime plus 2tv minus 1 equals 0. And now it's like a first order. In fact, what kind of first order is this? It's a linear first order, right? So this is t squared v prime plus 2tv equals 1.
You divide by t squared.
You have to divide by t squared, you get e, and that will give you your p in this location. You integrate by e to the ln of p. But you can actually realize here that it's actually in a nice form already. That's already a product. That's t squared times v all prime. So what would have happened is if you divided through by t squared, did that whole process, you'll end up with the integrating factor being t squared. You multiply through by t squared. You'll get back the original. So you can try it if you don't believe me. But here, I noticed that I differentiated the v, leave the t squared, differentiate the t squared, left the v. It's already in the product rule form. So I can just integrate both sides here. T equals a constant. And so I can end up with, here my v is equal to 1 over t plus ct minus 2. And of course we have to remember that our v is actually y prime. This means that y prime is equal to 1 over t plus c t minus 2, which means I can find y by just integrating that function, which is going to be ln of t minus c t minus 2. You don't really need the absolute values here because t is greater than 0, but why not? That's fine.
When you integrate again, you don't get a second constant.
We do get a second constant. Just put out plus d. So that's one case. We'll be revisiting this in a slightly more general sense, but if your y is missing, we can do some of that reduction of order even if your y is not missing, but if your y is missing, you have a very nice scenario that really often breaks down to just a first order linear, so that's nice. Here's another case. It's just a bunch of case studies here. This is a very important type of equation, by the way. This is called a Bernoulli equation. Bernoulli, a mathematical powerhouse. This is one of the families that they just had a lot of famous mathematicians in the family. Like the Bernoullis were just a math family. You had a lot of like big time mathematicians in this family.
Quick questions.
Yeah.
Is this the same Bernoulli that came up with Bernoulli's principle for flying, or is this a different one?
I don't know, but it's one of them. It's one of them. It's one. Someone in the family came up with that.
It's like
You have a bunch of Bernoullis that does they all did a bunch of different things. It's very confusing. Right? It's not like Newton. Okay, there was Newton. If you say Newton, everyone knows. Okay, it's talking about this guy. If you say Bernoulli, really have to check my history because there were a lot of them who did a lot of things.
There's a cool chapter in our book about all of these people. that
All the
discovered-
Bernoullis.
Well, just the people who discovered differential equations, starting in
Oh yeah, Bernoulli had a
He's
lot.
in there.
Equations of this form. They have a very specific form. So it's like they look like y prime plus p of t y equals q of t times y to the n. Right? Now, these need not be linear. Notice that if n equals 0, then what we actually have is a separable first order. If your n equals 1, you actually have a linear first order. Interesting things happen beyond that. For n greater than or equal to 2, here's what we do instead. We use a change of variable. We set v equals to y to the 1 minus n. Seems like a very strange thing to do, but let's actually see what's going to happen. Maybe I can jump to the next one. Show you how that substitution actually plays out. That guy is a nonlinear first order. It also happens to be a Bernoulli equation with my q of t equals to the function 1. Well, when I divide through by the t squared and move it to the standard form, the q of t would be 1 over t squared. So here, n equals 3. So what we're going to do is we're going to set v equals y to the 1 minus t. In other words, y to the minus t. Then, basically now I'm going to use that substitution. I want to plug that substitution into the equation.
Should we find y prime?
We should find y prime. What would y prime look like?
Negative y to the negative 1 times dy.
So here, dv dt, if I differentiate both sides with respect to t, I would get here negative 2y to the minus 3 times dy dt. Right? So that's our y prime. So in other words, if I write this as y cubed over minus 2 b prime, I would obtain y prime. Now, going in, plugging that in, I'm going to have t squared times minus 1/2 y cubed b prime plus 2t y minus y cubed. Now, notice what we can do here. The typical disclaimer. So we're not looking at the 0 function. I can divide through by y cubed, and you're going to see something amazing happen. You would have minus 1/2 t squared b prime plus 2t. If I divide y by y cubed, I would get y to the minus 2. Divide this by y cubed, I would get 1. Now you would notice here, there's a y to the minus 2. And what is that? B. Oh, that's our b. So now, this becomes my... See, I told you, right? Something amazing is going to happen. So this is v minus 1 equals 0. And now what is that?
Where did minus 1 come from? Oh, you got it.
Yeah, divided by the y cubed.
You could move the 1 over and it's
So first order linear. So whenever you have an equation like that, that's actually going to always happen. This changes it to first order linear in B. You just done?
Why does that happen?
It's just a matter of switching back and forth, I guess, no? Kind of.
Well, let's just get through this. So, what are we gonna have here? So this is minus 1/2 t squared v prime plus 2t v equals 1. Is that a nice thing for integrating factor?
But everything by negative 1/2 t squared.
Yeah, there was a quick way to actually get something going here. Let's say I multiplied by minus 2.
A little bit of minus 2 is pretty.
Is that nicer?
Should be minus 4.
Minus 4, yeah.
Minus 4.
Much better.
Not
I
really.
mean, I still divide by t squared.
Yeah. I was thinking if I could see a quick product rule, but let's just play it safe. Divided by t squared. And so mu equals e to the integral of minus 4 over t dt. This is going to be e to the minus 4 dt. This is going to be t to the fourth. This is going to give me t to the fourth times b all time equals, multiplying that by t to the fourth, I get minus 2t squared.
T to the negative 4, t to the negative 4.
Yeah. It's negative 2t to the negative 6.
So that would be negative 6. Integrate both sides.
One-third t.
2/5 t to the negative
Plus a constant. So this means that your v is equal to 2/5 t to the minus 1 plus c t to the fourth. This means y to the minus 2 equal to 2/5 t to the minus 1 plus c t to the fourth. That means y is going to be square root of that. Or can we put it up here? It's very clear. There's your solution. So yeah, you can see that working. It was really a genius just making the y just one less in magnitude than but in negative of the power of that guy, because then they realized, well, once we differentiate, we're going to get the minus 3, we're going to get the guy over there, which when we plug in, we can just multiply through by the y cubed and kill that y cubed. So that's how they kind of came up with the idea. They wanted to create a scenario in which they could kill that y cubed by multiplying through. So a substitution of y to the minus 2 seems to be a nice thing to do.
If we were on the test, would we put minus a 6 to 4 from y to the negative 2 to that 1 over, or would you accept if we stopped at like y to the negative 2 to 5 to the negative 1?
Where are you talking?
Right
This?
before you, yeah. Would you accept that, or would you want us to?
On a test, I think it'll be fine. But I believe on the quiz when I asked, I think I also asked this as a bonus point problem.
Yeah, you did.
It said y equals blah. So if it's indicated, just solve for y. But I mean, with a Bernoulli in general, you should be able to solve the y easier. It's going to be like a linear equation. And it's going to be easy. Here's another case. This is the last case we're going to do. Just going to spend a little bit of time on the second order. So let's say the independent variable is missing. So i.e. you have to form something that looks like y double prime equals some function of y and y prime. Meaning there's no like t or x. The independent variable is actually missing. Yes.
Is there a plus and minus on the top line?
Right here?
Yeah.
Yes, because I took a square root. So here, we also set v equals y prime, but we actually want to deal with that situation a little bit differently. But this time, the goal is to get y to be our dependent variable. Because we have no control over the t's or the x's. So, one thing you can do is that if your v equals dy dt, we're using t, I guess. Then what I can do is I can look at v prime.
D squared y is
dv dy times v.
Come again?
Can you say function?
I want y to be the dependent variable, so I'm actually going to look for
dv dy.
dv dy. Now dv dy is going to be what? Well, we can let that look like dv dt times
DDY?
dt dy. Is that the substitution I want to make? Because I want to be able to say,
We don't know what dt dy is.
well, it's 1 over dy dt, but I don't think that's what I want. I want to actually get that dy dt back. If I want to differentiate that with respect to t, dv dy dt. Yes, I think I do want this. That's going to be dv dy dt. Now we can make a couple substitutions. One, you can notice that if v is dy dt, then this is of course y prime, y double prime, right? And I also have the scenario that my v is actually the dy dt. So this I can write as dv dy times v. So this means I can replace my y double prime with this expression dv dy times v. And I can replace my y prime with V.
I have a question in that top line where you have v equals dy dt.
Yes.
If you look for, don't you just multiply both sides by d over dt to get dv?
Yes, but that means to take a derivative, right?
So yeah, don't you get like d dy on the top and then dt squared on top?
Yes, but that's not very convenient to express it that way. What I used here was the chain rule. I use the chain rule instead. It gives me a more convenient form. So now, with that, here's what we get. Start to sub in all these guys here. Let's do an example. So there's an example. There's no t's floating around anywhere. It's nonlinear. As you can see, we have y's multiplying each other. But that doesn't matter to us. What matters is that we have a second order and there are no t's anywhere. So what we can do is we can set v equals dy dt and set y double prime, so that's y prime. Set y double prime equals dv dy times v. By plugging that into here, we would get the following. Y times dy double prime
So you can get dy over v.
is dv dy times v plus this guy here is v squared equals 0. And you realize that it's going to be kind of weird to look at this at first. What you want to realize here is that the y now is your independent variable, meaning you're looking at it as if the v was the y that we've always been using, and this time the y is the t. So by looking at it that way, you realize here that we actually have a separable equation.
Yeah.
So I can do something like move this over, and I'm going to divide by the y and divide by the v. So I'm going to have dv. If I move the v squared over here, dv over v, and then if I move the dy over here, I would have minus dy over y.
That's really nice.
Right? So then I can integrate both sides. And so what I can get then is my v is equal to some constant times e to the minus ln y, or another way to look at that is like c divided by 1.
Is our goal to get y as our independent variable or dependent?
Independent. So it's the independent variable here,
So
right?
on
It's at the bottom of the derivative.
On the board, it's written on the green, the top board says to be our dependent variable.
Oh, that was it should be. Yeah, so we have that. And now what can we do? But what is our v?
V is dy dt.
Our v is dy dt. So here, separable again. I could multiply 3 by 2 and take a square root if I wanted, but let's see like this. Simplistic solution. Yes.
Can you explain how you got from the middle part of the top word to the integrals?
Here?
Yeah.
Okay, so I made these substitutions, which I derived by the chain rule. Then I just actually plug them in. I left the y alone. The y double prime I replaced with this thing. Then the v squared, the y prime squared is just v squared. So I have that. Now that's actually separable. So what I did was I subtracted v squared from both sides to move the v squared over there.
So
And then, what?
So what happened to the v squared? You made it dv over v.
Yes, because what I did then was I did like this cross multiply thing. So the dy I multiplied so it's on top.
V there.
The y I moved it down so it's on bottom. And then the v squared I divide both sides by v squared. So I have v over v squared, which is just 1 over v.
Yeah.
Yes. So try this one. And then we'll move on. I was going to say something about the existence and uniqueness for first order, but I'm actually moving pretty slow tonight, so I'll save that for some other time. Give you guys a couple minutes to actually try that one on your own. It uses the same technique.
So is it always that the v is equal to dy dt and the v double and the
Yeah, in the case that there are no t's, you can try that. Yeah.
oh, but that's
These-
always the case like in a, I mean for
Yeah, it's like a general case when you have a second order equation and your t's are missing. So you'd see your y's, you'd see your y primes, your y double primes, but there's no t anywhere. Right? So the fact that there's no independent variable lingering anywhere, you can kind of do this substitution.
Are there variations to that substitution, or is that just the one?
For this case, that's the substitution. That's the standard substitution. Variations would require a different kind of situation. But we can remember that in general, a second order differential equation would look like, in general, it's a function of this guy. So we looked at the cases where this wasn't there, where this wasn't there, and where this wasn't there. Right? So these are just some options, some things that might come up. Right? So of course, if you go higher order, you can have different things missing and different substitutions would come into play. But with this scenario, one of these missing, you can solve that equation by actually reverting it to a first order equation. And these are the standard techniques for getting that done. And we're going to start talking about these guys in more detail. We're going to be talking about them for a while, the second orders. Pick up a lot of important lessons from them. A lot of things with generalized a lot nicer. You know, it's kind of like when you're doing Calc 1 and Calc 2. Single variable calculus, everything kind of worked out one way. Then you go into 3 dimensions and suddenly everything all changes. Now I don't need to worry about limits from only 2 sides. I need to worry about it from an infinite number of sides, and everything just like went crazy. Then you learn to set up vectors, and once you actually set up that system, that generalizes very nicely to 4 dimensions, 5 dimensions, 6 dimensions. You can take all your forms and just extend them very naturally. Whereas that didn't work jumping from Calc 1 to Calc 2. But once you make the jump from Calc 2 to Calc 3, it gives you the power to do a lot of other things. First order versus second order is kind of going to be the same thing. things work one way with first orders, but when you get to second orders, they work in a different way. And they work in a kind of way that generalizes more easily to higher orders.
And lower
So
orders?
we're gonna, huh?
Does it also generalize lower orders better too, or is it kind of? our first
Well,
orders?
you would probably think of them as the first order being a subset of them, so it's like a restriction.
Okay.
But the methods that we learn on the second orders, we're going to be able to apply them to higher orders. And we'll also actually cover higher orders, but we're going to learn a lot about second orders, so we're going to stay on them for a while, 3 or 4 weeks or so. Okay, so let's actually get through this. So we're going to set our v equals y prime and our y double prime equals to dv dy times v. This means we would get dv dy times v plus g squared equals dv dt squared.
I have a quick question.
Yes.
So could you switch, you see the v on the dv dy, could you switch that v with the dy dt, possibly?
The v on the coming
You
in.
know how v is equal to y prime and y prime is equal to dy dt, right? No, you see how the v, like right up top, v is
Over
equal
here?
to y dt, yeah.
Okay.
Is it possible for you to switch that v on the new equation with that dy dt?
Oh, swap the v here with dy
Yeah.
dt.
Yeah, and then you get dv dt. I don't know.
Yeah, but that
Is that
that would mean that the t is now the independent variable. I want the y's to be the independent variable. I want the y's on the bottom.
Okay, so we'll just make it all complicated.
Yeah, because
Because
now
there's no t.
now you're like you have 2 independent variables in that case. Because you have something dy and then you have something dt. So
Okay.
sometimes like your differential with respect to y, sometimes your differential with respect to t.
Oh, okay.
Okay, so what can we do here? Huh? It's separable. Well, is it? No, it's not separable, because this is,
Oh, man.
Yeah. Do we set w to v squared?
You take a v out.
Yeah. Set w to v squared and then y would be.
come again?
You could set w to v squared and y could be written as a integral of v.
Could you use the Bernoulli equation?
Use your older approximation.
V2 to v minus 1.
Is this covered by the Bernoulli equation?
And you have to divide it in
What?
Is this the next topic? That we just bring it on this.
it's been a lot of time in this one,
Do we divide everything by v, and then
yeah.
do, the limiting factor?
No, but.
And then do what?
Isn't that the Bernoulli?
It does look like it.
What did the Bernoulli look like?
Then you like
F y v prime plus p So the function in front of v is just 1, and there's a function on the right that's qy, which is 2e to the negative y times y.
Yeah, but this isn't the right form.
Swap it.
Like, if we want to look like a Bernoulli, like I think you can do a Bernoulli here. You would actually multiply by, say, e to the y.
Oh no.
Right? Yeah.
But then you have a function in front of the differential. The Bernoulli form doesn't have anything in front of the.
Wait, why is it not the Bernoulli form? Could you explain?
You know what, because we don't have
I
a,
mean, to get to the Bernoulli form,
because we don't have a v raised to something on the other side. So
Yeah, but wouldn't the end?
No, but we could just divide by v and that would be it's v to the negative 1.
You know, but we still have.
Oh, yeah, right?
Yeah, if we divide everything by v.
Yeah, so it'd be dy, dv,
In
dy.
Bernoulli,
P
you
of t
said
would be 1.
v equals
P of t would be 2.
y to the 1 minus n. So can we treat v as the y this time and make a whole new variable?
And that'd be,
No, but what did the Bernoulli look like? It was y prime plus p of t times y
Y
equals
to n.
p of t y to the n.
and the n is negative 1.
Can we treat
Yeah,
v
these
as
guys
y
would
this
be
time?
negative 1.
Yeah.
Yeah, but then when you take the v of the other, is divided by v, would it be like a particular exponent? And that would
And
be
it's equal to negative
less than zero?
We can rewrite it as,
Why doesn't that
But I
work?
don't know what the parameters for that.
So if I do that,
You divide everything by v and then subtract the v to the right side.
Yeah, but wouldn't the v of the other side be negative?
But that wouldn't be Bernoulli's formula.
isn't Bernoulli only fine for positive n?
Equals 2.
divide by v.
Yeah, 2
We
e to
have
the negative
this.
y, v to the negative 1, and then n is negative.
Now y is
Oh, yeah,
v
no.
and v is y.
And then we're gonna set,
I have a question.
yes,
So we're doing a missing independent variable with this, with the Bernoulli equation inside it.
yes,
And then we're supposed to do this by ourselves.
yes. So now what is that gonna look like? What do we have to do another variable, right?
Yes, we could set w is equal to,
W,
yeah, y
V
1 minus
equals
2.
1 minus 2.
1 minus minus 1, which is 2,
Yeah, so
y2.
v negative 2.
Yeah, b2.
Oh, v negative.
Wait, is it a b positive 2?
it's the 1 minus
Minus
the
1.
n, right?
Oh, so it's 2.
Yeah, it's
So it's b squared.
That's what we started with.
And then,
wait, that only works if,
Wait, does this only work if it's greater than or
yeah,
equal to
greater
2?
than or equal to 2.
If n is greater
Actually,
than
you
or
said it
equal to
could be 0 or 1.
Or be linear.
Yeah, but
But
negative
it's
1
less
is
than
not,
0.
yeah, it's less than 0. It's less than 2, so it's not greater or equal to 2.
That's equal to
We could rewrite v as
and what would this guy look like?
v
v
2
2v
times dv
dy, and we know dv dy is y prime divided by
So if I plug this in,
wait, don't do the y prime.
Are you doing this to humor us? Because it's actually like a good idea. It's, you have dv dy, you can replace that with dw dy divided by 2v. Divided by 2v negative right?
and then we
Square
have
is
what?
w, right?
Then we have what?
W?
Yes, but we also have a v, right?
Oh, right, sorry.
And then what?
2e to the negative
Times 1 over v.
Yeah.
wait, now we have 3 variables. Wait, so how many of them are independent? Y is independent. W
So now if I multiply through by v, what's gonna happen?
You get v squared, which is w. And the.
Oh yeah, now we get W.
You have 1/2 dy.
So I have 1/2 dw dy
Plus w.
plus
W,
v squared,
which is
Which
W.
is w.
which is w. And here,
2d to the negative y.
Yeah, we could just write negative Y in terms of W, right?
and now what?
Now we're back to the same.
Same.
Oh, no, we're not.
No, we're not.
Get back to the same equation. Aren't you?
Oh, that's mu, it's trying to integrate it.
That's linear. Now it's linear.
Oh.
Sorry, you have all these letters, right? Okay, so keep going.
So wait, is this actually how you would do it? Or is there some trick we don't know?
So this is fine. This is fine.
So you multiply everything by 2. So you have dw dy plus 2w equals 4 e to the negative y. And then you
So linear factor, integrated factor would be?
E to the
no,
E to the 2w
into y, 2.
Yes.
Yeah, and then you integrate to e to the 2y.
So E to the 2y prime.
So now you have
Y
e to the 2y times w
All prime.
and prime, and this prime is with respect to y.
Right? Gotta keep track.
keep track.
Equals 4 e to the negative y times 2y, which is really the same thing as just
Times
e
e to the 2y.
which is just 4 e to the y.
So now we integrate both
Oh, now
sides.
it's so easy. Yeah.
Now we integrate both sides with respect to y.
You have e to the 2yw equals 4 e to the y plus c. And I divide both sides by e to the 2y.
That's 4 e to the negative
Cancel out one of
y.
those y's on the
And then plus c.
divided by e to 2, yeah.
And now you have to
Replace w and b squared. And then you,
W is equal to.
v squared,
Is equal to.
v is equal to y prime, so you can take the square root of both sides, and then you have y prime equals the square root plus or minus 4 e to the negative y plus c e to the negative 2y.
plus or minus.
Yes, or
You don't have to.
or e to the minus y plus c e to the minus 2y.
Yeah.
And then you integrate it again.
Yeah. With respect to
Now you have
t.
to integrate.
Yeah, t.
So you
No,
have
there is
t.
no t.
Yeah, good luck. It's
T is the original thing we're trying to find.
No, there is no t in the original function.
Right, that's the whole point, is you don't have t in the
Oh,
original.
yeah.
So you have dy and dt to the left,
So
right?
now you integrate.
Yeah.
You decide t. Because it's all in terms of y. You
So you
decide t.
integrate both sides. And
Well, technically it's separable. I don't think we should have gotten that. I don't remember getting a square root in my answer.
I did. But
You-
it's
you
not.
did?
Yeah, but I don't think I did.
I think it's equivalent.
Everyone is a-
So where do we? So here we got w, and w was v squared, and v was y prime.
Yeah.
I can't wait for him to do this in two steps.
And
Why can't we integrate both sides with respect to t?
Yeah, you decided t, right? Because it's only in terms of y.
Right, so then everything on the right is just constant.
Yeah. And then you plus c.
So you have y equals square root of 4 e to the negative y plus c e to the negative.
no, you can't do that because this is dy dt, which means technically you should be separating the variables.
So it's 1 over a.
So you'd have dy over that thing equals dt.
What if we go back a step to v squared equals all that stuff, and you subtract all that stuff, so you have v squared, and you turn v squared into y prime, so you have y prime minus 4 e to the negative y plus c e to the negative 2y equals 0. Does that help?
How is y prime 0?
Come again? Here?
Yeah, so there, you subtract everything, you make everything into homogeneous form, so you have y prime equals, or y prime minus 4 e to the negative y plus c e to the negative 2y equals 0.
It's not a y prime, it's a v squared.
But it is a y prime. V squared is, oh shit.
On the,
Oh, you're doing so good, you make one mistake, everybody laughs.
Like, no, like I don't remember ending up with a square root anywhere. So maybe just check that we actually did everything fine. So from here, d, y, we say da. 2b, d, b, dy. So that's 1 over 2v, that looks fine. We replace that guy with 1 over 2v plus the v equals e to the minus 2y.
When we were looking for W, why did we have to divide everything by V to begin with? Couldn't we just set W to V to the 1 minus 2?
No, because that here it's a minus 1. So they're using Bernoulli, so v is equal to 1 minus n, where our n
That's
is
the form
minus
it has to be in with the,
for Bernoulli, yes.
okay.
Did you know that for Bernoulli, you only make that substitution if n is greater than or equal to 2?
Yeah. I think
It works for if it's not 0 or 1. I mean, we got pretty far with it. What else would you do here?
I think that's why we're stuck if you use it when y n is equal to negative 1. I don't think we're allowed to do that.
Either way, you can do it.
This is not the form.
Y prime is dy dt.
I mean, is this going to be that bad?
It is.
Yeah.
What's it, integrate?
Yeah.
It's like working on arc length.
It's like what our working our
Worse than arc length.
So you can always put on the field and you can
That's probably like a trigonometric identity. We're just not seeing it. Sinh?
Don't say that. Don't remind him about this.
It's probably sinh or something. Because sinh is defined by e to the 2y. It has e in it. Sinh or cosine. It's one of them.
Yeah, no, I don't even want to go that far.
It's not useful.
You don't want to integrate that. That even you so you do it.
No, that's not useful.
Yeah, there's no use of
The factor out.
Wait, didn't we define y prime squared as being 2 something? Y prime squared?
Where?
You didn't define y prime squared. we
Oh,
defined
over there, y prime squared is 2e to the negative y minus y prime prime, and we know y prime prime is something with w.
I don't see where you
Middle, top board, middle.
If you rearrange the right next to the original example, if you rearrange it so you have y prime squared equals 2e to the negative y minus y double prime is d v.
And then maybe
I'm not sure that helps them.
we could go somewhere, because we're just stuck here. We can't
We still have to integrate it.
So you just find a different path and see if that takes us in further.
Integral calculator?
Symbol out, pull it up.
Yeah, okay, simple level crash.
I've seen simple like that before, yo.
Yeah, I don't remember getting anything like that, and I think I did a similar approach.
I think
Is
you
there
wrote
a
it down
syntax
wrong.
issue?
Did you write the problem?
No, I think that's the problem.
How do you know your work was correct?
So how do you use no substitution?
Can we start over?
Yeah.
So we did this. Yeah, y double prime plus y prime squared equals 2e to the minus 1. And our v was y prime. Y double prime is going to be dv y times dy dt, which is v. Plug that into that, we would get that.
For the Bernoulli equation, are you supposed to get like always a negative exponent or a positive as well? Or it doesn't matter?
As long as
I don't think that matters. As long as it's not separable or linear, I think you can So we have here dv dy v plus v squared.
Would it be W over dy?
I don't know where you're talking. I'm here.
No, I was talking about the line below that.
So now here I set w equals this guy.
Would it be the W with dv? Maybe?
I have a question.
No, you differentiate with respect to the independent variable, which is y in our case.
What if you take the last step of that, and we turn it into an exact, try to turn it into an exact. So,
Oh, yeah, partials.
right?
Where?
No, all the way to the end, the very end.
Y
Before you take, before the very last step, so you have y prime equals the square root of 4 e negative y plus c e. You're right. Yep, there.
Okay.
So what if you subtract, what if you first break apart the y prime into dy dt,
Okay.
you multiply both sides by dt, and then you subtract the right side from the left side, set it all equal to 0, and then try and set it up as an exact differential equation. So you have 1 dy minus all that stuff dt, and then you take the my and the nx and see if they are exact. And if not, see if we can find a way to include an integrating factor to make them exact.
Yeah, no, that's
Too much work.
There's no steps. No, it says there's no.
Do you know for sure what the answer is?
Yeah, I know the answer because I worked it out already.
Steps. Can we work backwards?
I don't know, I got, this is the answer.
No, it's not. It's too easy.
I think there's a problem with computers.
Oh, what? That's it.
Did you plug it into the question and make sure it's like correct? Because what if you made like a arithmetic mistake? You could try that, like just plug it in, make sure it's differentiated twice and then.
That's what I got. Anyways, just about, I'm not seeing how to dig ourselves out of this hole we dug ourselves into. So, I guess that's homework. But I'm pretty sure this is the answer, because I wrote it down and it made a lot of sense. Monday we don't have school. No one has class, by the way, Monday and Tuesday. So the next time I see you guys is Wednesday. And yes, I'll probably put this form on. See who figure it out.
Oh, we know the answer.
Oh yeah, that's right.
What else should we try? I'm gonna try it at home. Bernoulli didn't work. Should I just try everything else?
Whatever. Figure it out. Start like that. I threw away my work. I don't know. But I think that's really
Look at this
yeah, the quiz on Wednesday should be pretty short because we didn't really do anything besides exact equations with integrating factors.
And partial.
And what?
Functions with respect to partial differential equations. For the
No, just the exact equation with integrating factors and stuff like this, like reduction of order, Bernoulli. Yeah, I think that's our last.
Because I think we
I'll give you, but I won't make it. It's kind of like a partial.